11.5 Recursive Rules for Sequences. In this section, our goal is to evaluate and write recursive rules for a sequence, and then use recursive rules to solve real-life problems. Let's first talk about what is a recursive rule. Now, an explicit rule gives any term as a function of the term's position number in the sequence. This is the way that we have been writing rules. For instance, these are some explicit rules. This one, the first, is an arithmetic explicit rule, okay, where any term is found by multiplying 3 times the position of the term, whether it's the first term, second term, third term, so on, minus 2. The second explicit rule here is similar to our geometric rules, still gives any term as a position of where that term is at. For instance, if you were finding the third term, then you would put 3 in for the n. These rules are written explicitly. A recursive rule is written a little bit different than this. A recursive rule gives the beginning term, or sometimes terms, of a sequence, and then a recursive equation that tells how all terms after that first term or second term is related. Okay, so a recursive rule. A recursive rule, again, gives the beginning term or terms of a sequence, and then a recursive equation that tells how all terms after the ones given are related to the ones preceding. All right, to better understand, let's look at an example. Here in example 1, we have a rule written recursively. We're given the first term is 1, and then a recursive rule for all terms after the first term. Notice the a sub n minus 1. Anytime you see this in a rule, what this means is the previous term. It means take the previous term, the one before what you're looking for, the previous term, and do something with it. In this case, it wants us to take the previous term and square it, and then add 1 to it. So for this example, we are already given the first term. The first term is 1. Every term after the first term, you take the previous term, square it, and add 1. So when we're finding the second term, we would take the previous term, which was 1, we would square it, and then add 1. 1 squared is 1, plus 1 would equal 2. So the second term is 2. Now let's go to the third term. To find the third term, we take the previous term, which is the 2 here. We would square it, and then add 1. 2 squared is 4, plus 1 would equal 5. To find the fourth term, you take the previous term, which is 5, square it, and add 1. So 25 plus 1, we would end up with 26. Then the fifth term, which is the last one we were asked to find, we would take the previous term, which is 26, square it, and then add 1. 26 squared is 676, plus 1, we end up with 677. So our first 5 terms are 1, 2, 5, 26, and 677. Let's practice with this a little bit more. Let's look at example B. Notice in example B, the rule is written recursive again. This time we are given the first 2 terms. The first term is 2, the second term is 2, and then all terms after the first and second term, we are given a recursive rule. Notice this time that to find any term after the second term, we have a sub n minus 2. Now, if a sub n minus 1 means the previous term, then what do you think a sub n minus 2 would mean? This means go back 2 terms. So if we're starting at the third term, and we have to go back 2 terms, then that means go back to the first term. Minus the previous term, well, previous to the third term would be the second term. So to find the third term, what we need is 2 minus 2, or 0. So we have our first term is 2. Our second term was given to us, it's 2. And we use the recursive rule to get the third term. Now to get the fourth term, we would use the recursive rule again. We need to go back 2 terms. So we'll go back once, go back twice. So that means we're going back to the second term, minus the previous term, which would be the third term, and get our fourth term, which is 2. To get the fifth term, we need to go back 2 terms, which would be go back to the third term, which is 0, minus, go back to the previous term, which is the fourth term, 2. So 0 minus 2, we would end up with negative 2. Our first 5 terms then are 2, 2, 0, 2, and negative 2. Alright, I'd like for you to pause the video and give the next example a try. Let's show you what the next example is. Checkpoint 1, pause the video, give it a try, find the first 5 terms. Alright, hopefully you're unpausing the video and checking your answer. If you solved this example correctly, you should have found the first 5 terms were 3, 3 halves, 1 half, 1/8, and 1/40. If this is not the answer that you got, pause the video, check your work. If you're still not getting this answer, maybe go back and watch example 1 again. Alright, if you've gotten the correct answer, let's move ahead to example 2. In example 2, we are asked to write a rule for the arithmetic sequence where the first term is 15 and the common difference is 5. We're going to write this rule 2 ways. We're going to write an explicit rule and we're going to write a recursive rule. An explicit rule is what we learned to do in a previous lesson. Remember the arithmetic, an explicit rule for arithmetic sequence would be that any term would be equal to the first term plus n minus 1 times the common difference. So we substitute in what we know. We have the first term. The first term is 15, so any term is equal to 15 plus n minus 1 times the common difference. They've given us 5. Simplify, and we find that any term would be equal to 15 plus 5n minus 5. Put your like terms together, and we have the explicit rule that any term is equal to 5n plus 10. Alright, now let's look at writing the rule as a recursive rule. Now it's an arithmetic sequence, so it will always follow a pattern. In an arithmetic sequence, when you write a rule recursive, you will always give the first term, whatever the number may be, and then you would write a rule for any term where what you do is take the previous term and add the common difference. So, let's write this rule as a recursive rule. To write this rule as a recursive rule, we would need to first give the first term. The first term is 15, and then every term after the first term is found by taking the previous term, or remember, previous term is written as a sub n minus 1, plus the common difference, 5. That's it. That's all there is to writing this as a recursive rule. On the following slide, there is a checkpoint for you to give this a try. So if you'll pause the video Give this a try. You're given the first term and the common difference, and you're asked to write the rule as a recursive rule. Alright, hopefully you have paused the video and tried to give it a try. If you did this correctly, this rule written as a recursive rule, you would give the first term. The first term is -2, and then every term after the first term, since this was an arithmetic sequence, would be found by taking the previous term and subtracting 10. You might be saying to yourself, why subtract 10 when we're supposed to add the common difference? Well, this common difference was a -10, so you could have written plus a negative, but instead of plus a negative, let's just write minus. All right, let's look at geometric sequences. In example 3, I'm going to do the same thing. We're going to write an explicit rule and a recursive rule, but this time it's for a geometric sequence. If you remember from previous lessons, in a geometric sequence, any term can be found by taking the first term and multiplying it times the rate raised to the power of n minus 1. Since we're given the first term and the rate, we can write the rule. Any term would be equal to the first term, which is 4, times the rate, which is 0.02, or 0.2, raised to the n minus 1 power. And this is it. Cannot be simplified any further than this. This is a geometric sequence written as an explicit rule. Let's take the same information and write the rule as a recursive rule. In a geometric sequence, to write the rule as a recursive rule, you would give the first term. So whatever the first term is, you need to give that. And then you give a recursive rule for how any term after that first term would be written by taking the rate and multiplying it times the previous term, a sub n minus 1. So all we need to know is what is the rate and multiply it times the previous term. So this rule written as a recursive rule, we know our first term. Our first term is 4, and then every term after that first term is found by multiplying the rate, which is 0.2, times the previous term, a sub n minus 1. That's it. This is the rule written as a recursive rule. All right. Pause the video, give this checkpoint a try. Again, you're going to write a recursive rule, this time for a geometric sequence where you've been given the first term and you've been given the rate. So write the rule as a recursive rule for a geometric sequence. Alright, hopefully you've paused the video and given this a try. You should have written the rule as the first term was equal to -2, and then every term after the first term was found by taking the rate, -3, and multiplying it times the previous term. That's it. There's the recursive rule for a geometric sequence. Maybe better to put this in parentheses so you don't get confused that that's a minus sign or something like that. Let's make it clear that it's multiplication. Alright, let's look at example 4. In example 4, we're asked to write a recursive rule for a sequence. So we have to come up with our own pattern. So it's going to take some trial and error. You would look at the first term, and you see, is there anything that you can do to the first term to get the second term, the third term, the fourth term, the fifth term, and so on. One way to get from the first term to the second term would be to multiply by 1. 1 times 1 would give you 1, but then that wouldn't get you from the first term to from the second term to the third term if you're just multiplying by 1. So that's not quite it. You could try maybe adding or subtracting, maybe adding 0, but if all you're doing is adding 0, that still won't get you to the third term. So it must be a little more complicated than that. try seeing if you can do something with the first term and the second term. Maybe this rule involves that they've given you the first term, and you may need to even give the second term, and then what can you do with the first and second terms so that you can get the third term. You could try adding the first and second term, but that won't give you the third term. 1 plus 1 would only be 2. You could try multiplying, but 1 times 1 would only give you 1. Maybe you need to add them and then multiply or divide by something. So try maybe add 1 plus 1, and then what could you multiply by? 1 plus 1 would be 2, and then to get 4 we would have to multiply by 2. So then try, that gives us the third term. Let's try how we could get to the fourth term. So what we said was we took the first two terms, we added them, and then multiplied by 2. So now let's take the second and third term, add them, try that pattern of multiplying by 2. 1 plus 4 would give us 5, add 2, multiply by 2, that does give us the 10. So check it out, does it work for the next set? So this time we would want to add 4 plus 10. That's 14, multiplied times 2 does give us the 28. Try it for the next set, 10 plus 28, and then multiply that answer times 2. 38 times 2 does give us the 76. So we see that our rule is working. So what we are doing is, to get any term after the second term, we're taking the two previous terms and adding them, and then multiplying by 2. So how do we write the two previous terms? Remember, to write the two previous terms, we need to go back 2 terms. So we want n minus 2 plus, we want to go back to just the previous term, that's n minus 1. And then we want to take that sum and we want to multiply it by 2. So we want 2 times a sub n minus 2, a sub n minus 1. So when we write this entire rule, the first term is given, the second term is given, and then every term after the second term is found by multiplying 2 times the sum of the two previous terms. This would be the recursive rule for this sequence. Alright, now I'd like for you to give it a try. Write the recursive rule for the sequence 2, 3, 8, 63, 3,968, and 15,745,023. Pause the video, give it a try. Alright. To write the recursive rule for this sequence, you should have said that you were given the first term, and then every term after the first term was found by taking the previous term, squaring it, and then subtracting 1. Let's go on to example 5. In example 5, we have a word problem. It says, a nursery initially had 500 trees. Each year, it sells 70% of its stock. It adds 500 new trees. We want to write a recursive rule for the number of trees at the beginning of the nth year. Well, let's look at first our percent here. We're selling 70%. If we sell 70%, then the amount that we keep, which is what we want to write a rule for, the amount that we keep then would only be 30%. 30% of our initial stock. And then we also add 500 trees. So, to write a rule, this is part A, we would start by giving what our initial amount is. Our initial amount was 500 trees. Then at the beginning of every year after that, we don't have the 500 trees anymore. We sold 70%, but we kept 30% of that initial amount. So 30% of the initial amount, well, remember that's the A sub n minus 1. That represents the previous year's amount. And then we also add 500 trees. So this would be our recursive rule that represents the number of trees at the beginning of the nth year. Now, we also wanted to find how many trees would we have at the beginning of the 5th year. So we want to find what's the 2nd term, the 3rd term, the 4th term, until we finally get to the 5th term. Now, using our calculators, we want to put in 0.3 of the previous amount, which was 500, and then add 500. So using our calculators, we can find that in the 2nd year, beginning of the 2nd year, we had 650 trees. If you leave that 650 on your calculator, then all you have to do is take that answer, multiply it times the 0.3, and add 500, because the answer on your calculator is always your previous answer. So take the 650 that's already on your calculator, multiply it times 0.3, add 500, and you should find at the beginning of the 3rd year you have 695 trees. Leave that on your calculator, multiply it times 0.3, add 500, and you find at the beginning of the 4th year that you would have 708.5 trees. Now, if this is where we were stopping, we would say that this is 709 trees, but we want to go on to the 5th year. In the 5th year, we would do the same thing. We would take that previous amount, 708.5, we would multiply it by 0.3 and add 500, so that at the beginning of the 5th year, we would have 712.7 trees. We can't just have 0.7th of a tree, so we would say, even though it may be a short tree, 7/10 of a tree, we would say it's still a tree, so we have 713 trees. Alright, let's look at Part B. In Part B it says, what happens to the number of trees at the nursery over time? If you continue this pattern, okay, we already know what 1 through 5 are, but you continue 6, 7, 8, 9, 10, and so on, and you continue this pattern where you're multiplying the previous answer by 0.3 and adding 500, you find that at the 6th year you have 714 trees. It's actually going to be some decimal answer, but it's 714.12, so we would say that's 714 trees. At the 7th year, you multiply that by 30%, add 500, you find at the beginning of the 7th year, you have, again, 714 trees. This time it's 714.2, but we'd say that's 714 trees. At the beginning of the 8th year, multiply the 7.14.2 times 0.3, add 500, you see that you still, again, have 714 trees. It's still 714.2. So what we find is that over time, it stabilizes at 714. Alright, let's look at the checkpoint. I'd like for you to pause the video, give the checkpoint a try, do just part 1, then unpause the video, check your answer. Alright, hopefully you've paused the video and given part 1 a try. You were supposed to write a recursive rule for this situation. Your recursive rule should have been that the first term was 1500, and then every term after the first term should have been found by multiplying 0.63 times the previous term and adding 300. If any part of this confuses you, it's probably the 0.63 here, okay? But if we are losing 2% of the trees from dying and another 35% are sold, then we're losing 37% of the trees. If we're losing 37%, then what do we keep? We keep 100% minus that 37%, or 63% of the trees are kept. And our rule represents the amount that was kept. Alright, pause the video, give part 2 a try. In part 2, you want to know how many fir trees are on the farm at the beginning of the 6th year. So you'd want to take your calculator and use the recursive rule, find at the beginning of the 2nd year, the 3rd year, the 4th year, and so on. What you should have found was that at the beginning of the 6th year, there were 897 trees. Part 3 asks you what happens to the population of fir trees over time. To figure this out, continue the pattern, multiplying by 0.63 and adding 300, and you should see that over time it will stabilize. If you've done this correctly, you should have found that over time it stabilizes at 811 trees. Alright, just like I did in 11.4, I've included the homework answers so that for those of you who've been away on the trip, you will be able to check your work. Remember, no work, no credit, so these are just the homework answers so that you can check them. Okay, here's 22 to 28. Take a moment, check your answers. You may even want to pause the video so that you have time to check them. Okay, and move on. 30 to 34. You'll need to pause the video to have time to check them. This is 30 to 34. 30, 32, 34. Okay. Alright. Here's 36 through 44. Again, you may need to pause the video to have time to check them. When you're done checking them, unpause. And then here's the last of the homework, 56 to 70. Again, you may need to pause the video to have time to check them and then unpause it when you're done. I will see you in class.